Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Chris Jackson. We're talking about reliability testing, noting that we often, Fred in particular, because he's caught the ire of a listener, bashes reliability testing and says the results are meaningless. And the listener asks, well, what makes a good reliability test? Which is a great question, by the way.
Yeah. No, it called me out on it. Said you've talked about how, example after example after example, and I do have many of them. Testing in general, but reliability testing in particular, is just not useful the way it's being implemented. And so he called me out on that, and I'm trying to find the source of the question, so I have a name associated with it, but I'm not finding it. But anyway, I did give an answer and sent back some info, but it was, and I'll start with a bad example. The organization required that every round of prototypes you do halt testing.
Right.
It was a requirement from the organization, from somebody that said that could impose that on the development team. And they had a beautiful halt lab, and I knew the people that ran that, and they were excellent engineers, and they really did, they even went the next step and tried to sort out did the failure analysis and looked at making recommendations. They wrote up a beautiful report. And the director of engineering just stacked them up next to his door if he wanted to prop his door open to his office. He never opened them. The binding had not been messed with at all on more than 20 reports. And even though the test itself, the halt exercise was done very, very well, in my opinion, it's of no value whatsoever. It's a waste of time if the people that have the charter to actually act on it and make design improvements just don't even look at it, just don't believe it could actually be useful. And so that's one of many issues I run into, is that you got to start at the start. Who needs what information? And if testing's the right way to get it, let's make sure that test will create the information that helps that person either make a decision or understand an issue or, or discover failures. But if the audience is not going to use it, it's a waste of time. And then vice versa, there's plenty of really bad tests that are, well, just throw it in a chamber and hope for the best. Well, yeah, hope's not a plan, I guess.
Can't you size up in the question a little bit where it sounds like those halt tests you're actually advocating in the example you gave, well, they were great lab facilities, but it was an issue whether the leadership was bought into those results, which is a whole different podcast in its own right.
Well, I agree with that as a problem, but why run the test if it's not going to be used? And vice versa. If I had this the other day, I only have 2 samples. How do I prove statistically that it lasts for 20 years? Well, you're not going to get there from here, with just a test. If 2 samples, you got to run it for like 80 years and then hope it still doesn't fail. But even that won't show it with hardly any confidence.
Right, but you could still use those 2 prototypes in conjunction with, if you've done a robust FMEA or fault tree analysis or whatever, so what the vital few weak points are. You might have field data. You might have been able to analyze through finite element analysis. And with any data you do get from those 2 things, where you might do target accelerated life testing on a particular part of that component, you might be able to still generate confidence that thing's going to last 20 years.
No, I agree.
But you're talking about the pure statistical approach, aren't you?
Yeah, they wanted just pure. Can you help me figure out a sample size to show that this device or module, whatever, is going to last 20 years? Yeah, there's lots of ways to go about doing it. How many samples do you think you can get? 1, if I really push it, maybe 2. Right? We need to have a different discussion now.
Right.
But I've seen way too many people say, well, we're just going to use the 2 samples we have and kind of wave off the confidence intervals and say that we showed it. And like, okay, what's the failure mechanism? Well, what do you mean failure mechanism? We don't want any to fail. Okay. Well, what stress are you applying? Oh, we're just heating it up a little bit, but not too much. We don't want to go out of spec. Okay. Well, how long are you going to run it? Well, only a week because that's all we have. Okay. So now you're showing that one or two products can last a week at just slightly above your upper specification. And they go, how do I convert that into 20 years? Well, that's a wave of the wand, I think. That's not anything that a statistician can do for you.
Right. I mean, that's where I've already designed the test. Can you tell us how to parlay it as something it's not? And
Right.
that's obviously a tight question. But I think you're talking. So that's an example of a useless reliability live test.
Yeah.
I'd argue. I think
See,
it's
I'm
also,
really good at those. I have way too many examples of those, I guess. It's my nature. So
but
it's appropriate I got called out on it.
and I'll go another direction. I've been involved with, especially with militaries, a bunch of really wonderfully statistically significant demonstration tests with hundreds of data points, hundreds of failures. But here's the thing. Because they're reliability demonstration tests or product reliability acceptance tests, by definition, they get done on production-ready prototypes.
Mm-hmm.
So the problem with that is what happens when it fails, which they invariably do, because as soon as you have a reliability demonstration test, especially in a very bureaucratic organization, then that becomes the patron saint of reliability. Reliability is going to be okay. Why? Because we have a 2-year reliability demonstration test. Fantastic. We'll wait till then to worry about reliability. But by the time that comes, when there's something that goes wrong or something you realize is not as reliable as it should be, you're done. You're locked in. Even if the flow chart allows you to has this arrow which goes back to preliminary design to redesign certain things if it fails a demonstration test, you don't have the schedule or money left to do that.
Yep.
Or the cultural impetus
Yeah.
because there's so much investment personal, if nothing else, into getting it to that stage, you're done. So that's another useless test in that no matter what the numbers spit out, they're going to be pulled apart and cut and say, well, that one doesn't count because that pothole was 2 inches bigger than regulation. This one over here, we believe we've designed that out of the system, so that one won't count. All of a sudden, we got a product that's going to last forever.
Yep.
Beautiful. Well done, team.
Yeah.
So, and of
Yeah.
course, there's
It
bad news
doesn't.
stories that result.
Yeah. Well, to outline what I think is if you're going to do testing, any kind of testing, I use the poor examples as illustrators of this, but the framework when I think of about going testing is what question am I trying to answer? What piece of information am I trying to generate? So for example, my director years and years ago, and when I was working in a team, said we need to show by testing that our new product here will last 20 years buried in concrete and it was a heating element that would go in bridges and it would melt. It had sensors on it for temperature and moisture and it would keep the bridge dry. And they didn't want it to be less than 20 years because it's a big, huge concrete bridge in the mountains and that's really expensive to tear up and replace the heating elements. So they wanted to make sure it would last. And I said, well, how do I do that? But at the start, I had a timeline. I had plenty of samples and resources. We had chambers, all the other good stuff. I had to get some, measurement systems and things to monitor the product as it was going. And I had to learn how to do the analysis for this degradation test that we were running. And it was very clear that we need to show with 90% confidence that it will last for 20 years above some threshold of power output. But I wasn't coerced or coached or whatever to say, well, that's not, I got plenty of help in designing the test and in any of the troubleshooting and sorting out how to get this chamber to hold the right temperature, stuff like that. But when it came to the end, we walked through the analysis and said, yep, that's all sound. That makes sense. And I was taking a bunch of statistics classes at the time at a local university and ran it past my professor and he goes, oh, well, this is great. So I had a lot of I'm using air quotes here, confidence in the analysis and in the test design and so on. And was able to back that all up with here's the assumptions. I checked for this, I checked for that. I made sure the temperatures were right, all this other stuff. And I had a chemist involved to help me sort out what the actual activation energy is. And then we saw anomalies with that. We understood what was the chemical phenomena that was occurring that caused that slowing of the degradation. And it was all pretty tight. And it took me about 6 months to run the test. And we presented it to the customer and walked through the setup and the logic and how we analyzed it and everything else. And they goes, great. And they signed it up and they bought millions of dollars worth of product. And to me, I had a clear question that I needed to answer. And it was either yes or no, right? Either it's going to be good enough or in that middle gray area where, well, it could be good enough, but we're not really sure. Or it could be clearly not good enough. And it was very clear that it was good enough. And so we were able to answer that question very clearly and with substantial evidence and backup on the theory and the chemistry and the physics of what was going on and double checking all the analytics, that it answered the question. And so it was, oh, we have a chamber, let's go do a test. Well, we only have temperature, so we're going to do that. Well, I knew that I had a chemical process of oxidation causing chain scissioning in the polymer chains. It was breaking the chains with oxygen. And so I knew it was a chemical process. And instead of assuming an activation energy, which is another hallmark of a poorly designed test, I went to the chemist and said, here's the phenomena that we think is happening. And he confirmed it. And then he said, can you tell me for this particular structure, what's the activation energy? Oh, yeah, I got a test that can run that. And he ran it wasn't an accelerated life test. It was some chemist wizardry they did. He said, oh, it's a 0.73. Okay, great. I was off and running. I don't remember what the actual number was.
Yep.
But that's a good test. It starts with you have something you need to know and somebody that wants to know that. And then you work with that person to say, well, how well do you need to know it? Because I could answer this test with engineering judgment, which is pretty crude and it may or may not be right. It's just my judgment. But you can have an answer today. Or I can spend 6 months and run a bunch of tests and experiments and all the other work to make it happen and give you a fairly accurate, it still has uncertainty with it. Which would you rather have? One is going to cost us, $250,000 and one's going to cost you about 10 cents.
Yep.
So, it's way too often that I see we have a chamber, we're going to use it. Okay. Do you need to know anything that chamber any information that chamber with your product is going to provide you? No. Well, the chamber is pretty worthless then, isn't it? How about we figure out what you need to know, and then go from there. And it's not usually the reliability person's fault. It's a combination of the expectations of what they're supposed to do, what people are not clear about what they want, all those other things. But I think in order to design a test, I equate it to an experiment. You have a hypothesis, you know what you're looking for, and you know enough about the phenomena that are involved so that you apply the appropriate stresses and you're monitoring the appropriate things. That then gives you a way better chance to create a test that has a lot of value.
I think I talked to you recently in podcast about this other scenario where 3 DC converters were being assessed for their reliability. And I was approached by the young reliability engineer who essentially said, well, how do I know which one to pick? I keep being told zero failure tests are really bad. And I went, yep, can be. Let's talk about it. And essentially, he ran an accelerated life test where he was able to simulate 3 times the service life of the device or the machine that was being. And then he said, well, 2 of them didn't fail at all within that accelerated life test and one failed, but just towards the end. And so I said, so long story short, these things, two of these things showed that if you were to run a device or machine for 3 times the service life, you're pretty comfortable that those exact DC converters in the same way that we use this time, that'd still be working. And the third one would be probably fail towards the end of that, third iteration of the service life. And absolutely, that's what I believe that, because he also knew the technology involved as well. And so I said, well, we can also, are you confident that none of these are going to fail during a single service life interval? Absolutely. I'm confident that none of them are going to fail. He said, well, you don't need to test for reliability then, do you? Because these aren't going to cause your system to fail. You've just proven that your system's going, when it does fail, be failing due to something besides these DC converters. So pick the cheapest, lightest, best looking one, or whatever it is, or the one with this from the supply chain with the least risk. So one of those beautiful times where you don't have to do, let's call it the statistically valid test that sometimes gets rammed down our throats. And it all comes down to what decision are you trying to inform. Sometimes we're asking ourselves, what's the likelihood of this thing failing in our service life? And the answer is, from the test, is even though they're not statistically robust from one perspective, in that if you're trying to estimate the time to failure and the distribution of the probable times to failure for those DC converters, you don't have much to go on. But that's not what the question or decision's being based on. It's being based on the likelihood of them surviving this first arbitrarily small period of time. And when I say arbitrarily small, I mean arbitrarily small from the perspective of how these things degrade. And so the reason why you want to understand, like you said, the question you're trying to answer or the decision you're trying to inform, is a good chance in many cases you could save yourself a ton of stress and money, because you don't always have to do that exhaustive, statistically significant test. And then you just move on with life. Sometimes people need to hear that from a reliability engineer before they feel confident and just essentially going, okay, we're cool.
Yeah. No, I get that. It's one of the things I have a hard time with the success testing is, well, it failed near the end. And if you really want to, and I'll use the example I use all the time, is if you want to show 90% confidence that you're at least 90% reliable, and you can replicate a lifetime or even 3 lifetimes. If you do 3 lifetimes, then you only need 7 samples. 3 is still not enough to show a 90-90. And 90% reliable is usually not adequate for a lifetime of a product or a component or whatever. But let's say, for the sake of argument, that because I can remember these numbers, that you have 7 samples and they run for 3 lifetimes, except one of them doesn't quite make it, and that becomes a slippery slope. It failed at some point. The test was designed with the stresses to replicate the experience of the product over its lifetime, and then you do it 3 times. Now, the math works out that it's saying, what's the chance that 7 samples will survive 3 lifetimes, with the underlying assumption that the extra lifetimes doesn't invoke a different failure mechanism. All right. There's an underlying assumption there that makes that valid, which isn't always a good assumption, but that's what we do. And they say, oh, it almost made it, but it failed. So we're going to waive that and say it actually passed. But in reality, that means that that underlying unknown distribution has a less than 90% chance of being successful overall. We're estimating the population parameters, even though it's only 7 samples. But by going out 3 lifetimes, we're really probing into that tail to some extent. Now, there's a ton of assumptions that go under that, that makes that tenuous at best, in my mind. But what I find is that somebody says, well, 6 of them passed, but 1 didn't make it all the way out, so that's good enough. Well, let's redo the math now, because now you've changed the design of the test. So now you're at a 70%. You've shown that it can go 70% of reliable over 1 lifetime. Is that good enough for you? And if it is, why didn't we start the test with that criteria? So Yeah, you can shade it. You can say, I don't like that one. Oh, that was customer abuse or, whatever. It's no, then you haven't shown what you set out to show. I agree with you, Chris, that it's if you understand the technology, you understand the use of it, and you know that there's other components in the system that are more likely to cause problems, then don't worry about it. In which case, I would say, why are you testing it? Let's go to those vital few that you really don't know much about, or are life limiting. Let's go test those and to really get information.
So, I mean, so to answer the question, I mean, what makes a good reliability test? I think we've touched on a few things. I think the first thing is one, are you the sort of person, or is the boss the sort of person who wants to know what the reliability is or know what the characteristic is of the product that informs a decision? Or do they just want to be told it's okay? If they want to be told it's okay, then you have a problem because that's the main aim. They're asking you to try and find a way to tell them it's okay, as opposed to genuinely knowing the characteristic in question. So it's a mindset thing. That whole test to learn versus test to pass thing
Yep.
that is mentioned a lot. The second thing I'd suggest is a good reliability test is not one that's just done due to dogmatic reasons or standardized reasons. Oh, we have to do a demonstration test. Why is that? Because that's how we do it.
Usually you hear
No,
it's in the contract.
yeah, which is, and that all but guarantees a terrible outcome because it's in the contract. And often those tests that are mandated in contracts are resource intensive. And that means they become the focus of so much reliability effort. They suck the oxygen from the room
Yep.
of everything else. It just becomes, okay, that's the reliability God we're worshipping. It'll be tested later on. No need to do reliability now. And of course, all testing does is measure how successful your efforts were versus replacing those design and manufacturing efforts. So the first one is, do you want to be told it's okay, or do you want to actually understand the characteristics? Second one is, are you after a standardized test? Sorry, are you crafting a test to answer your question, or are you relying on, history, standard? Okay, the standard says we need to do this, and off we go.
Oh,
So that's
85, 85. I could do a whole
right,
podcast just on that one.
right. That's the second criteria, and the third criteria is, I'd argue is maybe we go back in the steps. Do we need to test? Sometimes the answer is definitely yes, but if you can answer, if the question is the answer, sorry, default answer is, well, of course we need to test because we need to test. You hear that a lot, or
Yeah.
variations of that answer a lot.
Yeah.
Okay, why? Well, you just do. But why? And it could very well be a good answer if they've sat down to work out what the reason is. But sometimes you don't need to test. And that, if you have a good answer for why you need to test, you say, for example, okay, we do have tons of field data for this component, but this is the first time we're using it in this system. And we're concerned that perhaps a vibration profile might be different, et cetera, et cetera, et cetera. All of a sudden, you've won me over. Okay, you know why you're conducting a test. But then you also, in that answer, you've already worked out what it is that's going to keep you up at night, and that's vibration.
Yep.
And
And
so
now
all of
you
a
know what
sudden that
stress to
fit
use. Yeah.
right. And so that's the third thing is, have you actually worked out if you're going to if testing is going to give the information you need? Or so that of itself is a symptom of actually thinking about whatever it is you're trying to get on top of. So that's three. What about anything you want to add to that list, Fred?
Well, the last piece I would add is make sure you check your assumptions. Well, there's more. There's do the failure analysis too. But the analytics and the test design stuff is we don't have the answer yet. So we're going to make some assumptions that it's this failure mechanism or that it has this pattern of failure or this distribution that describes it. We'll check that. Make
Yeah.
sure, things like I mentioned, solar activation energy, and way too many people just pick a number out of the air and hope it's close enough or conservative or whatever. And like, that really, really, really makes a huge difference if you really do have a chemical based process going on here. If it isn't chemical process at all, then what are you doing with this formula? Is the test design and the underlying assumptions that come with the design true or true enough that you'll get a reasonable answer at the end of the day? I mean, simple things like if you're going to put something in a chamber and you say it's at 100 degrees C, well, is it? Did you check? I went through 20 different chambers where we found one that was within 5 or 10 C across the cavity of this thing. And then we ended up modifying it so we got a bit better airflow through it. So we got within 2 C of our target. Um, we take, oftentimes it's get the stuff in the chamber and let's go. And it's at the end of the day, you get results you really don't understand. And then you turn out and somebody says, that upper right corner is at 400 C. We're supposed to be at 100 C. Maybe that's why they all failed up there. And it's like, so just like setting up an experiment in a science lab is, if you're going to be measuring the response to some chemicals, don't have residual unknown chemicals in there. You might end up with something you don't want. It's do due diligence, do a good experiment on top of everything else. And then the analytics is do good analytics, which includes checking the assumptions. So those are all parts of it. I love it when somebody says, we got results, but I don't know what it means. Well, that's actually an indication of a very poorly designed test. If you get vague or unknowing results, then you could be that it's great observations, or it could be a really poorly designed test. So anyway, I guess it's in my nature to talk about bad tests all the time because I have seen and done some that are just not all that useful, but being aware of what it takes to actually get good information out of all of that expense of doing a test, I think is critical. And it does take thinking and working up front and checking assumptions and paying attention to the details. I don't think there's a way around that.
So that'd be number 4, rigorously research and then state and understand your assumptions, which I
Yep.
heartily agree with. I think the 5th one is don't design a test and then ask someone to give you the answers you want. And that includes
that's a plague for statisticians. I had more than one person figure out I was doing a lot of stats, and they'd walk in with a whole pile of data and say, "Could you tell me what this means?" Well, what'd you do? I did a bunch of random measurements. Okay, well, you have a random pile of junk there. That's all that is. They weren't happy with that.
No, and I think we're going back to your scenario where you have someone tell you, I've got 2 prototypes. We have one chamber that only has heat. We can only control the heat, no vibration. So we're going to test these 2 prototypes in an environmental test chamber where the only lever we pull is heat. Tell me this is going to last 20 years. So that'd be the 5th one. I think just designing your test and working out, and then working out if it's going to answer any questions or help you answer the question. And that often happens when you've got this sort of mindset on progress, procedural, process zealot saying, or not even process zealot, just someone we need to move on as quickly as possible. What is the most we can do without upsetting my schedule or budget? Done. Reliability engineer, tell me this is all good. Sorry, sir, you cannot do that.
Can't do that. Now it's so anyway, we outlined a handful of things, and you realize that the last one was, do a good experiment, take care of the details and stuff like that. Is that it's a lot about the upfront stuff. What's the question? What's the constraints? What's the precision you need? Do you even need a test? All the other stuff. And then once you have a firm grasp of what kind of information you're trying to create to answer a question or inform a decision, then you're in good shape to go actually do something useful. And there's still constraints. You're still never going to get enough sample sizes. You're never going to get enough time and all the other good things that happen. And there's lots of ways, once you understand what you're trying to do, there are multiple ways to answer that to varying degrees of accuracy or precision. But just running off and throw it in a chamber is not the way to go do it. So start with what you need to know at the start.
Yeah,
Well, that was a
absolutely.
question. As we're chatting here, I'm scrolling through this list of questions I got, and I go, oh, we answered that, and so I'm sorry I couldn't find the person that sent it in and give them credit for the question, but it's actually a good question. Well, how do you do a good test? So we should probably think about that a little bit more and probably do a webinar or something on it. But if you're listening to this and you got a question, or if we missed something in the steps to create a good reliability test of some sort or another, let us know. Head over to accendoreliability.com/go/SOR. There's a couple of ways to get in touch with us there. Chris and I and the other hosts of the show are available through LinkedIn and through our About pages on the site. We have plenty of ways for you to get in touch. So it's time to go, I don't know, throw a bagel in the microwave and see if I can get something close to toast. That's my experiment for the morning. It's early,
Right.
guys.
So, yeah, well, that's you started what success is, so we're already off on a good start.
Yeah, there you go. All right. Great talking to you, Chris. I'm glad I ran into this. I know it was a while ago that we got this question, but I thought, this would be a good one with Chris. I don't think we've talked about this one before.
No, that is a good question. It's a really good question.
Yeah, and there's more out there, so we're looking forward to it.
And it shows people are paying attention.
Yeah, well, we tried to. All right.
Right.
Thanks, Chris. Talk to you soon.
Cheers, Fred. Always a pleasure.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.